All right, so today we're going to talk about the notation of mathematics, specifically of algebra. We're going to start getting into what algebra is, how it can be used to help model some situations. You're not going to hear me say that this is something that you're going to use for your future occupations. That is not necessarily the case, but it is something that's developed independently all over the world and naturally occurring. So it all started with this idea of counting things. Back in the day, they wanted to keep track of their cattle. They wanted to keep track of, the days and nights and how many days had passed before the next time it was going to rain, and look for those patterns. So they just found a system to count, and that wasn't always with the numbers as we know them, 1, 2, 3, 4, 5, 6, but they were using some sort of symbol to do that. And as the numbers got larger and larger and larger, there was the creation of symbols that stood for more than one unit. And we do that by now putting a 0 behind something and then putting a 1 in front of it. And we say that that's a tens value. So this single digit represents one set of 10. And in its essence, that's a multiplication on its own. So how did this multiplication come about? So they're counting those values, and if there was a more efficient way to do something, then that's what they were going to do. Now, this isn't going to be a really large number because I don't want to take the time to draw several hundred dots, but I can do this, and instead of going 1 of these, 2 of these, 3 of these, 4 of these, 5 of these, 6 of these, 7 of these, 8 of these, 9 of these, 10 of these, we've learned that we can use a multiplication strategy, which says, oh, well, there are 5 of them here, and there's another 5 of them here, and another 5, and another 5, and another 5. And really, we're doing 5 plus 5 plus 5 plus 5 plus 5. And I'm going to throw another set on here because I don't want this to be confusing about which number means what. But and then we have another set of 5, so another plus 5. So what do we really have? Well, we have the repeated addition of 5. 5 plus 5 is 10. 10 plus another 5 is 15, plus another 5 is 20, plus another 5 is 25, and plus the last 5 being 30. And we could just add over and over, but there was a much easier way to notate this if we introduce the idea of multiplication. And we write that as 6 times 5. But we didn't always write it that way. You probably saw the first multiplication problem of this exact quantity would be 6 times 5, but the multiplication was written with an x. We are not going to use that, and one reason we're not going to use that is because we are going to deal with x, and it means something different for us, and we want to make sure that we don't get this confused for that letter x in our expressions. So you might see parentheses sometimes. You can notate it that way. You might even see just a dot. And so when we say 6 times 5, what it really means, again, is 5 plus 5 plus 5 plus 5 plus 5 plus 5. And we now know that value is 30. We have the means of finding that. So this is multiplication. It's saying we have 6 of that amount. But there are instances where we are going to have what's called a variable. And what if we had x plus x plus x? Let's just leave it like that. X plus x plus x. We are adding x how many times? 3 times. And so we would write this as a multiplication, just like here was 6 times 5. We're going to write 3 times x. And that is going to look like this. We just write 3, and then we put an x right behind it. And it's important for us to know that the 3 is telling us how many times that x is being added together repeatedly. And this, when written like that, is 3 times x. We read it as 3x, but you need to know that this says 3 times x, or is interpreted as 3 times x. And it's just our notation. When you were born, you did not know that this meant multiplication, nor this dot, nor these parentheses. But as we've gone on through our schooling, we've learned that. If you haven't grasped it yet, 3x will be 3 times x, and you need to recognize that so we can use it in our future. We're going to look at some notes here. In modern mathematics, we use algebraic notation to represent situations that involve both blank and blank quantities. So I've already mentioned one of them that's new to us, specifically because we're now in algebra. The first day of school, I actually brought in the term algebraic, and I compared that to expressions that were just numerical. And using the idea of what numerical means, we should be thinking that numerical is numbers. Numbers that are identified using our number system, 0 through 9. Every single number that you're aware of can be represented with these digits in some pattern. That's numerical. Algebraic will involve the introduction of something called a variable. And I would like us to focus on what that means. Vary, V-A-R-Y, means what? If you think of some words that have that as their root, like a variety, so multiple different things, various, same sort of idea, or the weather that varies. Some days it's hot, some days it's cold. It varies. It means change, and that's what a variable is doing. We can't pinpoint, not always, pinpoint what the variable is as a value, or that variable is representing not just one value, because that value is changing, and what we're calculating is going to be probably dependent upon that value. So we just keep changing it as we see fit. Sometimes it can represent all numbers all at once, and that's kind of crazy. But we have variable quantities, but we also have numbers that don't change. And you are used to using those, but you're probably not used to calling them by this title. But if we have part of an expression that doesn't change, like the number 5 does not equal 4, nor will it ever equal 4. 5 is what we say constant. It is a value that doesn't ever change. So we have constant quantities, but we also have variable quantities. Working with algebraic notation fluently, and that's a good word to use here because I've talked about how math is really its own language. And if you're not understanding the symbols, the words, the notation, you're going to not have a good time reading and writing and understanding that language. And many of us are starting that journey right now, and algebra is a big part of that. So we're going to study this language, and we're going to focus on what does it actually say, and if we need to translate it into something that we do better understand, we should do that so that we have a better grasp on what is really being said. But if we can do this fluently, it will allow us to reason abstractly about complex situations with ease. And this is a reality. It allows us to take sometimes a real-world situation and turn it into an equation that we just solve like we're tying our shoes, and then our answer to that equation can now then be transferred back into our real-life situation. And it felt like it was no trouble at all, because tying our shoes is no trouble at all, because we do it all the time and we have a strategy for doing something like that. So back to this. A variable is a quantity that is able to, and I've mentioned this, but a variable is a quantity that can change in value. Oftentimes, maybe it is not a changing value, it's just an unknown for the time. But we, when given an equation, can figure out what that is, or maybe what possibilities it could be, because it's not limited to just one number at times. For example, if we allow x to be the variable that represents the number of people in the main gym during a basketball game here at the high school. You know, that number of people does not stay consistent all the way throughout the game. At tip-off, there might be less people, fewer people. Halftime, people are going out to the concession stand, they're going to the bathroom, timeouts, all sorts of reasons why people be shuffling in and out of there. So the number of people in that gym does not remain the same. All right, so here's another vocabulary word. We're going to use this one a lot. It is a blank can be used to simplify an expression of repeated addition of a variable. Okay, and this only happens with a variable. We don't call it this if it's not telling us about the repeated addition of a variable. So in the example that I gave earlier, I did x plus x plus x. This right here is that number that identifies how many times we're going to add x to itself. 3 times here. And that number that I just mentioned is called a coefficient. That's a little sloppy. I'll rewrite pieces of that, but coefficient. It's a great name for it, the efficient part anyway, because that's what it does. It makes us more efficient with, instead of having x plus x plus x plus x plus x, if we recall the notion of multiplication as repeated addition, we can re-express, we can take this right here, and we can write it simply as 5x. And that means we're doing 5 times x. That means we're doing x added to itself 5 times. In this notation, what did I emphasize? That the 5 is doing to the x. What operation is represented with this notation? Repeated addition, yes, but it is a form of multiplication. I can write it better than that. Multiplication. Furthermore, we can interpret the expression 5x in a couple of ways. One of them is going to make a little more sense to us because it's more concrete. You can think of it as x taken 5 times, as we kind of said here. You know, it's x plus x plus x plus x plus x. Or, since multiplication has this commutative property, what is the commutative property? Well, 3 times 4 is 12, and 4 times 3 is also 12. So if we thought of this instead of as 5 x's, you could think of it as x number of 5s being added together. However, that's kind of tricky because if I don't know what x is as a value or it's changing, then I can't really write it out. Because how many times do I write it? I don't know because I don't know what x is. So more likely, your brain will probably attach to this sort of representation there. Let's look at the bottom of this page here, and we're going to start applying it. So there are a few things we do need to know that may be general knowledge, but let's make sure that we understand. We're imagining we're at the park, and we are going to let x represent the number of traditional bicycles. So what do I mean traditional bicycles? That means we have the 2 wheels, and we have 1 seat, and you know your handlebars and whatnot. So 2 wheels, 1 seat. That's what this is. And we're going to think about those properties as we talk down here. A tricycle. Now I'm going to have a more difficult time drawing a tricycle, but a tricycle, I'll do it kind of from a view where you're looking over top of it a little bit. This is the seat, I guess. This is the handlebar. These are the back 2 wheels. I see a tricycle in my garage, but I've never tried drawing one before. So that's a tricycle, right? We have a wheel here, we have a wheel here, wheel here, and it's getting worse as I keep going. And there's a seat there. That's a tricycle. W is going to represent a unicycle. So W would be A unicycle looks like this. There's like a seat here. It's just down on a stick, and there's just a wheel. You've seen those if you've maybe ever been to a circus or some sort of act. And then Z is going to be what we call a tandem bicycle or two-seat tandem bicycle. And that would be, well, it is defined as a bicycle. So it does have two wheels. However, it is a two-seat bike. So if you've never seen one before, it's pretty neat. But there are two seats. There are two people who ride it. They work together to pedal the same bike. So there's a seat here, and there are the two wheels. Okay? This is the important information that we need to know as we go down and try to do this. So first, we are trying to come up with a way to express the total number of tricycle wheels at the park. And so if I ask that question right now, if I said, hey, how many tricycle wheels are there at the park right now? Hopefully your answer is, I don't know, because you shouldn't know that answer. You would know that answer, though, if I said, hey, there are 7 tricycles at the park right now. Now you could be like, oh, okay, well, there are 7 tricycles. Every tricycle has 3 wheels. So how many wheels that belong to tricycles would there be at the park? And you could do 3 times 7. You could count those in different ways, but the most efficient way would be 3 times 7, and you get 21. But now what if I changed it and I was like, oh, no, I'm sorry, there aren't 7 tricycles. There are 9 tricycles. Well, now we would say, okay, there are 9 tricycles. We still take it times 3, and that would tell us that there are 27 wheels that came from tricycles. From those 2 examples, what I want you to realize is that we're going to take, however many, Y amount. That's what this is saying. There are Y amount of tricycles. I don't know how many there are, but whatever you tell me, I would take that number and I would multiply it by 3 to get the number of wheels, specifically the wheels, for the tricycle. And how would we represent that expression? Well, looking through our list here, and I don't have it all on this page, it still continues, but 3Y, that would be, Y is the number of tricycles. We times it by 3, and that would tell us the number of wheels for the tricycles every time. So this is going to be letter A. And I can put a check mark here that I've used that one. Now let's look at B. The total number of bicycle wheels at the park. Well, I want us to go back to our definitions of what these letters, these variables, are representing. Because I don't know about you, but Y, which represents tricycles, the number of tricycles are not bicycles. So we would not be using Y in this rule at all to help us figure out how many bicycle wheels there are. The same with W. W is a unicycle, not a bicycle. So it's only X, which is a traditional bicycle, and Z, which is a 2-seat tandem bicycle, that would be used in my expression. And so once again, I want you to think about how many bikes do we have? I don't know that answer right now. We're going to call it X amount. But if there were, let's just give us a hypothetical situation. If there were 5 bikes that are traditional bikes, how many wheels would that account for? Well, if every bike has 2 wheels, and there are 5 of them, that would be 10 wheels. The 10 is the number we're looking for. How did it come about? Well, we took 2 times the number of traditional bicycles. So we're looking for, something that says 2x. And then there's more. There's beyond these wheels from the traditional bicycles, there's also the wheels that belong to these 2-seat tandem bicycles. Because even though they're different types of bikes, they still are bicycles. And that would be 2 wheels for every one of those, too. 2 wheels for every, and this is represented by the letter Z, or the variable Z. We should get in the habit of calling them variables now. but this will tell us how many wheels there would be. If you tell me how many regular bikes there are, traditional bikes, and you tell me how many tandem bicycles there are, this little rule, which by the way is this one, B, will explain how many wheels there are for that scenario. Now, hopefully you've gotten a little bit of the idea. You're going to continue with the rest of this and see if you can match these up. See if you can get them all figured out. And if you do get that figured out, there's an additional little practice sheet to help you establish more patterns with this type of thinking, still along the same idea. So that's it. I'm going to let you guys get to work. Hope you guys have a good weekend.